Hello and welcome. In this video, we are talking about redox titrations. This is where we're using electrochemical reactions that we've balanced in stoichiometry. For a redox titration, it's important to realize that it is not the same thing as an acid-base titration. We do have a similar goal in mind, but it is a little bit different, and we do need to be careful that we are not using acid-base terminology, so keep that in mind as we go through this and when you reach your formal lab report. It's still a titration. The goal of the titration is still to determine the unknown concentration of the analyte. We'll still have a substance of known concentration in the burette. We call this the titrant. So our titrant would be in the burette that we see over here. And we titrate what we have in the burette with a substance of unknown concentration. That unknown concentration would be our analyte, and our analyte is generally down in the flask that we see here. We are still titrating to the equivalence point. The equivalence point is the point where the moles of each of our reactants are stoichiometrically equal to each other. So this is a tiny bit different than what happens in an acid-base reaction. In an acid-base titration, that's where our two reactants have neutralized each other, where our acid and base have neutralized each other. If it's not an acid-base reaction, it is not a neutralization reaction, and so it's just where, again, those moles of reactants are stoichiometrically equal to each other. It is important to realize that the equivalence point is not the same thing as equilibrium. Whenever we do a titration, we are still titrating to the end point. So the end point ideally should be at approximately the equivalence point. However, it's a visual indication of that point where we're stoichiometrically equivalent. We pick an appropriate indicator so that our endpoint is approximately at the equivalence point. When we see that color change, if we pick the correct indicator, we should be really close to that equivalence point or that point where our two reactants are stoichiometrically equal. So let's talk about reading a burette again. Remember, burettes are different than most of our glassware. Burettes are read from the top down, not the bottom up. So at the top of our burette, we're starting with 0, and then the burettes will be using our 50 milliliters, so that 50 milliliters would be at the bottom. So let's look at an example, reading the burettes that we have here. The image on the left shows a burette of potassium permanganate before the titration, and the image on the right show an image of the burette after the titration. So remember, when we're reading the volume in a burette, it goes from top to bottom. We also have to make sure that we're estimating one digit beyond what is marked so that we're following our sig fig rules here. So when I look at this burette, I see my line for 5, this larger line here is for 5.5, and then I got my line for 6. So our meniscus, we want to read at the bottom of the meniscus there, is falling right between 5.6 and 5.7. So I know 5.6, or I know that tens place with certainty. We have to estimate one digit beyond what is marked, so we're estimating the hundredths digits. It looks right between that 0.6, 0.7 line, so I'm going to call it 5.65 milliliters. At the end of the titration here, we are between 37 and 38. I got a line for 37.1, 37.2. We're like right on that 37.3 line. Again, the burette is marked to the tens place, so we have to add one more estimated digit. To me, it looks right on that 37.3 line, so I'm going to make my estimated digit a 0. Then the important part here is knowing how much potassium permanganate was added to the flask so that we can determine the moles of potassium permanganate that we used. So final volume minus initial volume will tell us how many milliliters of potassium permanganate we did in fact use in this titration. So we find that 31.65 milliliters of potassium permanganate was added. So when you come to do your redox titration next class, you do want to be sure that you are following these rules to read a burette and especially measuring the correct number of sig figs here. Let's continue on and look at an example of a redox titration. We have a solution of I3- and it's standardized by titrating AS406 under acidic conditions. We're titrating 0.1021 grams of the AS406. This has been dissolved in 30 milliliters of water. And we know the volume of I3- solution it took to reach the equivalence point. We're given the unbalanced equation. Well, to do a redox titration, we're going to need to do some stoichiometry. First off, we're going to have to balance this reaction. Part B asks us to identify the species oxidized and the species reduced. Well, we already split up those half reactions by oxidation and reduction, so we can just look back up here to see that our AS406 was oxidized and the I3- reactant was reduced. So moving on to part C, we want to calculate the moles of the AS406 present in the initial sample. We need our balanced chemical equation because we're going to be doing some stoichiometry here. When we look back up at our problem, it tells us that we titrated 0.1021 grams of the AS406. Well, this first problem only wants moles, so this is just a simple molar mass conversion. Once we've completed that molar mass conversion, dividing by molar mass, making sure we keep our 4 sig figs, we find that we have 2.580 times 10 to the negative 4 moles of our tetraarsenic hexaoxide. We want to find the initial molarity of that tetraarsenic hexaoxide. Well, molarity, or the concentration of that, is our moles divided by liters. We just solved for those moles. And if we go back and look up in our problem again, we can see that those grams were dissolved in 30 milliliters of water. So we need to divide by our volume in liters. We still get to keep 4 sig figs in our molarity. We should find that we have 0.008601 molar AS406. Moving on to part E, we want to know how many moles of I3- were needed to reach the equivalence point. Now we get to do our stoich. We know from our molar ratio that every 1 mole of AS406 requires 4 moles of I3-. Well, we know how many moles of AS406 we started with. We need to figure out how many moles of I3- were required to completely react those moles. Again, we would start with the moles of AS406 we know that we reacted and use our mole ratio to the I3-. We have a 1 to 4 mole ratio. That shows we need 4 times as many moles I3- as we had AS406. So 1.032 times 10 to the negative 3rd moles of I3- were added to reach the equivalence point. Then we want to find the concentration of that I3-. Again, concentration is moles over liters. We know our moles of I3- that we just solved for. We can go back and see in our problem that it required 36.55 milliliters of I3-. We do need to convert that to liters by dividing by 1,000. And this will give us our molarity of that I3-. Should find that molarity to be 0.02824. With any lab, such as a redox titration, we need to talk about and understand potential lab errors. The first potential titration lab error is over-titrating. When we over-titrate, we go past the equivalence point by adding too much titrant. We need to know how this is going to affect our data. If we add too much titrant, it's going to take more to reach our perceived equivalence point. We're going to say that we used more moles, so it's going to look like we had more moles of our analyte. So whenever we use more moles of titrant, we're going to calculate more moles of analyte. If we have more moles of analyte divided by our original volume of analyte, it's going to appear that we had a greater concentration of our analyte. The opposite error would be under-titrating. When you under-titrate, you add too little titrant. If you add too little titrant, your calculated moles of titrant will be too low. And if you have too low of titrant, we use that mole ratio for my titrant to analyte. Well, those moles of analyte would be too low as well. When we take our moles of analyte divided by its volume to find the concentration, our concentration would be too low. Another common error is when water is added to the titrant. So this could happen if the burette is still wet from rinsing it. So if there's still water in the burette, when you go and fill it with the titrant, that's going to affect the concentration of your titrant. The titrant is supposed to be the thing of known concentration. But if we accidentally get water in this thing of known concentration, that's going to dilute it. We're going to have a lower concentration. If we have a lower concentration of our titrant, in order to get it to completely react the analyte, we're going to end up using a greater volume. If we use a greater volume, that's going to seem like we use more moles of analyte because we're still working off of that original concentration that we thought our titrant was marked at. If we calculate more moles of titrant, we'll have more moles of analyte, causing a higher calculated concentration of our analyte. On the other hand, if water is added to the analyte, so the thing of unknown concentration, if our flask or beaker is still wet, whenever our analyte is an unknown solid, we still have the same exact amount of analyte. The moles of our analyte are not changing. If the moles of analyte do not change, we need the same moles of titrant. There is no effect on the concentration of that analyte. So you might experience one or more of these errors in your lab report, and that is something that you will be able to explain when it comes to your formal lab report. So we'll talk more about these errors in conjunction with your lab next class. Before we reach there, we have one more practice problem. Go ahead and pause the video, give this redox titration a go on your own, and resume when you're ready to see the results. In this titration problem, we are titrating I3- with some thiosulfate ion. So we have the balanced equation this time, so we don't need to go and balance one. It tells us how many milliliters and the molarity of our sodium thiosulfate that we used to titrate the I3-. We had 15 milliliters of our I3-. We're trying to find the molarity of the I3-. In order to find the molarity of that concentration of my I3-, we're going to need to calculate our moles of I3-, and molarity is always moles divided by liters. Well, to find my moles of I3-, I'm going to need to do stoichiometry based on the information that was given to me about that sodium thiosulfate. Well, we're given a volume and molarity. First step of stoichiometry is that balanced equation, which we have. Then we need to get to moles. Using volume and molarity, I can get to moles through multiplication. When I multiply my volume times my molarity, I will get my moles. I left my volume here in milliliters because the volume of I3- was also given to me in milliliters. So this is a problem where millimoles can be our friends. So when we go back here and we multiply these, we find that we have 12.01 millimoles of sodium thiosulfate. We need to go from this sodium thiosulfate to our I3-. When I look at my balanced chemical equation, It has I3 minus to just the thiosulfate ion ratio. So our first step in our stoichiometry is going to be getting to just the thiosulfate. Every 1 mole of sodium thiosulfate is going to have 1 mole of just the thiosulfate ion. Now that we have only our thiosulfate ion, we're ready to use the mole-to-mole ratio that we have in the balanced chemical equation. We know from our balanced chemical equation that every 2 moles or 2 millimoles is going to react with 1 millimole of I3 minus. From this, we will find that we had 6.005 millimoles of I3 minus. As we mentioned earlier, to go and find that concentration, we are going to need our moles, or in this case, millimoles of I3 minus. And we can divide it by our volume of I3 minus in milliliters. Millimoles, we'll call the milli part to cancel out. We'll end up with moles over liters, giving us a concentration of 0.4003 molar for our I3 minus. So there you have it, some redox titration stoich. Looking at number B, letter B, we are analyzing our error here. After performing the titration, the student determines that the molarity of I3 minus that they calculated was larger than the actual. We want to know the most likely source of error. Take a moment and think about those sources of error that caused our molarity to be larger than it actually was. Whenever our molarity is calculated higher than it actually was, that is almost always due to over-titration. Over-titration is when we add too much titrant, which causes moles of titrant and moles of analyte and concentration of analyte to appear to be too high. So again, over-titrating, which means we're going past the equivalence point, is going to cause that I3 minus molarity to be too high. If we titrate past the equivalence point, this volume of titrant that we used is going to be too high. That's going to cause our millimoles of sodium thiosulfate that we said we used to be too high. And if that millimoles is too high, our moles of I3 minus that we calculate is too high, causing our final molarity of I3 minus to also be too high. So you will be performing your redox titration, which is your formal lab for the second 6 weeks in class next time I see you. Looking forward to it.